It's time to go to University of Washington. The first presentation from University of Washington, Dr. Travis THONSTAD is going to talk about exploring the combined use of distributed fiber and deformed bar reinforcement to resist shear forces. Dr. THONSTAD.
Thank you so much for that introduction. And can you see my presentation okay?
Yes, that looks great.
Okay, perfect. Well, thank you so much. So today I'm here talking to you about macrosynthetic fiber reinforced concrete, and my co-PI in this project is Paolo Calvi, also here at UW. Thank you for the opportunity to make this presentation today. So why are we talking about fiber reinforced concrete and accelerated bridge construction? So FRC enjoys widespread use in practice. It's already required in several states for bridge decks. And you know, the improved serviceability and durability that you could see in prefabricated bridge elements made from FRC could create an additional incentive for owners to choose ABC techniques over other alternatives. Now, PBEs are already have great durability, but certainly fiber reinforced concrete is another way to improve those further. And there's obviously last presentation, it was wonderful to hear all about some of the work that's being done at Nevada Reno. What I'm talking to you today about is not steel fibers, maybe not carbon fibers, but instead macrosynthetic fibers. So these are polyolefin typically, and they still have some structural properties, but they're not necessarily the same thing as what you would see if you had steel fibers. And there's some benefits in terms of construction as well with these, but they tend to provide increased durability and ductility for the concrete, better crack control. Those are all things that we knew already. And one of the things that we're exploring with this project is there an opportunity with these macrosynthetic fibers, which are easy to incorporate into your concrete mixture. Could these help alleviate congestion and reduce the required amount of deformed bar reinforcement? So we're not saying that you're going to completely eliminate the deformed bars because these fibers just don't have that type of strength, but could you supplement those bars with these fibers, and in doing so, make your construction simpler, easier, faster? And the challenges really are that strength contribution isn't recognized by the code, and part of the reason for that, and I'll show that in just a minute here, is that we really don't have a lot of test data about what strength these fibers provide and how they interact with the deformed bar reinforcement and the strength of that. And so the project objective is going to be to develop these rational design equations for the contribution of macrosynthetic fibers as supplementary distributed reinforcement. So the supplementary is the key word there. So looking at the previous research here, you can see that the figure on the right here shows the number of tests that have been conducted, and on the x-axis here is the decade. And so you can see that most of those bars are gray colored, and those are tests of steel fiber reinforced beams without stirrups. And so you can see that's the majority of the tests that have been done to date. And that's of course allowed us to have some code provisions for steel fiber reinforced concrete without stirrups. And a much more limited number of beams have been tested, or specimens have been tested, including both fibers and stirrups, and those are shown in the blue boxes. The light blue boxes are steel fiber reinforced concrete, and the dark blue boxes are using these polyolefin fiber reinforced concrete. So you can see the number we're talking about here of tests that have been done with both polyolefin fiber reinforced concrete and stirrups is very, very low, on the order of less than 10. And so the other issue we see with this research is that they're typically all these tests have been done on beams, and that so we're not just isolating the shear behavior, but we're also seeing the flexure behavior as well. So we can't decouple the two of those in these tests. And so if we think about, so one of the tests to point out, why go through this? And this is the test that motivated a lot of this work. This is a test done to look at the effects of fibers on beams. And it was an interesting test in that they had a experimental matrix that consisted of 4 beams per series, and one beam in the series had no fibers and no longitudinal reinforcement, just plain concrete. No fibers and no transverse reinforcement. It's just a plain concrete beam with longitudinal reinforcement. It had one beam with just fibers and no transverse reinforcement. It had one beam with transverse reinforcement and no fibers, and one beam that had both transverse reinforcement and fibers. And so in doing so, what they were able to do was isolate in some way the contributions of the fibers, the stirrups, and just the concrete itself. And so, but that's what you're seeing here in the graph to the right. You can see there's both a test series that was done with steel fibers and a test series that was done with synthetic fibers. So we'll look at the bars on the right. And the quite curious thing about all of this is you can see the fibers have some small contributions, not as large as if it was steel fibers, but there's this interesting box at the top there, which is that hatched region, which they named synergy, which is really just the extra strength that you saw in the beam with both fibers and transverse reinforcement that wasn't accounted for by the strengths of the other beams that didn't contain both. And so that's what we're really trying to look at in this series of tests and this investigation. So going back to the shear resistance of a beam, we know there's contributions from a number of different sources. And really what we're looking at in this case is there a contribution from those fibers crossing the crack? And can we quantify that and codify that? And like I said before, beams have been the typical way we've done this. Unfortunately, that involves both flexure and shear, and so there is that coupling that we have to deal with. One way to isolate that is to instead look at a shear panel. And if we take a panel of concrete that's rectangular or square in plan, and we subject that to pure shear, then we can investigate just the shear behavior of that panel. And that's a wonderful way to look at the shear behavior of a composite material like reinforced concrete. However, you need some specialized equipment. And so that is one of the wonderful things about our lab here at the University of Washington. We have this panel element tester. And so this is what that looks like here. So you can see we have a number of both conventional data acquisition, non-contact instrumentation. But we will start here with the frame. You can see a big rigid steel frame here in gray. Then you can see the panel there in the middle, and attached to that panel are a bunch of links, 40 links in all. Those are attached to actuators, which are able to control the in-plane stresses that are imposed onto that panel. And so in this series of tests, we're looking at subjecting them to shear. You can see that we have our LED targets there, and you can see that, of course, we have some hydraulic systems there that are controlling this all precisely. So the research program really has three phases. The first one was to develop a database of tests of macrosynthetic fiber reinforced concretes, also steel fiber reinforced concrete elements with both deformed bars. And so that's been done. You can see sort of the results of that in that bar chart from before. So we have those now, and we're looking into the next phase, next two phases here. One is performing experimental tests, which is looking at a series of panels that have macrosynthetic fibers and also deformed bar reinforcement. And of course, we would like at the end of this to come out with some new design equations on the shear strength of macrosynthetic fiber reinforced concrete. And we really need to base that on some rational shear behavior model, considering what the data that we've collected in our database and also this new data that we're collecting in our lab. And that third phase needs to be based off of the existing, there's a lot of existing empirical formulas that can be modified. Certainly there's some finite element modeling that we're doing currently, which is going to be exploring that as well. So a lot there as well. I'll talk about that briefly at the end. So today, because this is ongoing, this is something that we've been working on, I'm going to talk mostly about the experimental tests, and we'll talk a little bit about the third bullet here at the very end. So we have a test matrix. We have a series of panels here. The panels have different volume fractions of fiber. So that's the first column there in VF. 0, 2.26, and 0.52. Those are corresponding to about a typical dosage ratio recommended by the manufacturer and the maximum dosage recommended by the manufacturer. You can see that the longitudinal reinforcement ratio, rho X, is constant throughout the panels, and then we're varying the amount of transverse reinforcement, rho Y. What does that look like in pictures? So you can see these are the panel specimens now. If you have 0 transverse reinforcement, you can see the test region here is in the middle, and you can see as we go up to the amount of transverse reinforcement, we just add additional bars. And the volume fibers, again, you can see the addition rates there, 4 and 8 pounds per cubic yard. What kind of fibers are we using? We're using the GCP Strux 9040. So those are 40 millimeters in length. You can see the dimensions here. They're kind of a tape-like fiber. They have a high modulus, which is why we selected them, and have a decent tensile strength. So these are pretty long fibers and tend to have reasonable properties, been used in a lot of previous studies. This is what specimen fabrication looks like in our lab. You can see the casting table there, the steel anchor blocks. Those are what allow us to attach the reinforced concrete panel to the test frame. You can see the fiber addition and the curing there. So once you get this panel cured and for at least 28 days, then it comes into the panel element tester. You can see some of the weight. I'm basically just going through the process here since the data is still coming in, but just to give you a sense for what we're doing and why we're doing it, to give you a sense for this type of research. We're tracking the position of the panel, the deformations within the panel using these LED targets. Again, we're applying some known state of stress. We're measuring the state of strain, so we're able to then use that to develop these behavior models. There we go. We also have conventional instrumentation. It's really just there as a backup, but of course, it's always nice to be able to compare the two and see that the things are relatively lining up well. We trust the non-contact instrumentation well, but of course, if there's some obstruction or something gets in the way, you can sometimes lose those targets. So it's nice to have a backup just in case. Here's what you see, just a typical panel test. You can see we're subjecting this to pure shear. So you have to push with one set of actuators and pull with the other. And that produces that diagonal shear stress there. Because of that, you can see the cracks are oriented mostly vertical, which is great. That's exactly what we want to see. Eventually, this localizes and you get one big crack all the way through the middle. But you can see, there's a crack mapping that's going on here, and so we digitize that. So we'll have these sorts of plots to show. And that's important, I should say, for fiber reinforced concrete, especially because we'd like to compare those crack widths to the non-fiber reinforced panels. So far, the good news is that everything seems to be making sense, which is always the first step here. So the previous study, you can see there's 3 tests there in the green, sort of the 2 brown colors. Uh-oh, something's going on. And the panels that we tested without fibers, which would be comparable except for the reinforcement ratios, those are lining up with what we'd expect. So that is great news. We are still processing the data for the fiber reinforced concrete panels, and so unfortunately, that will have to be for the next research days. In terms of some of the things that we're doing in addition, so obviously each of these panels has fiber reinforced concrete. We're looking at the properties of that fiber reinforced concrete, looking at the residual strengths, trying to correlate that to the strengths that we observe in the lab of the panels. In terms of the progress, you can see we have now tested 6 panels. We processed the data from 2. We've constructed that 7th one there. We're in the process of the 8th, and we're moving right along with the testing. So what's next? So we're going to develop these new equations for the shear strength of macrosynthetic fiber reinforced concrete based on this rational shear behavior model. So you can see here at the bottom, what does that look like? It's the modified compression field theory. You can see the sort of the standard pictures there. And so really what we're coming down to is how do you modify the concrete constitutive behavior in order to account for the addition of these fibers? Do you have to account for anything else? And so certainly, previous test series have investigated steel and synthetic fiber reinforced concrete for panel tests. That's something that's been done, and certainly have calibrated those. One of the things that's a challenge is that none of those tests included deformed bar reinforcement. So how does that interaction, that synergy that was so important in that test series, how do we capture that using this modified compression field theory, which is perfect because that's what's implemented in the AASHTO code. So that's what we're hoping to do here. obviously, again, there's a lot of empirical relationships existing already with a lot of this test data. And so can we evaluate those using the data we've collected, the data in the database? And is there things that we can do to tweak those, to modify those, to then use them to predict the strength of elements with both fiber, macrosynthetic fiber and deformed bar reinforcements? And the last thing is to use finite element modeling that incorporates modified compression field theory to extend the results of this ongoing experimental testing. That's in progress right now. And so with that, I'd like to say thank you. Appreciate the time to talk to you today and update you on the project. And I hope that I can come back later and give you the updates on the results as they come in.
Thank you very much, Dr. Thonstad.
Appreciate it.
Yeah, I noticed that shear testing device which you guys used on another for UHPC.
That's right. Yeah.
Shear properties. That's really valuable piece of it. I have a couple of questions. Let's see if we can answer it in the next 2 minutes.
Sure.
It looks like, I guess in your presentation, you talked about one type of fiber. The question is asking, do you plan to look at other type of fibers?
Yeah. So that's a great question. I should have mentioned a little bit more in the presentation there. So that's great that you picked up on that. So we're looking at this one particular type of fiber because it has some properties that we think are beneficial. Certainly, there are a ton of fiber manufacturers out there, and there's a lot of products to choose from. And so thinking about the material testing that we're doing in parallel with this panel test, those are really meant, the idea behind all of this is eventually to get some kind of performance-based spec so that you can say, okay, you need to have a residual strength of X in order to get this type of, and that's already done with the code provisions that they use steel fibers as well for strength. So I at this time we don't have, there's just one extra variable to investigate, but certainly the hope would be that the results are general because they're tied back to this performance-based type of specification. Okay, thank you very much, Travis. Always pleasure attending your presentations.